All right, let's get started. Good morning, everyone. Today, we're going to be talking about asymptotic notation. This is sort of the culmination of all the math stuff we've done in the course so far. First, we talked about proofs, then specifically those nasty proofs involving quantifiers and inequalities. And then we took a sort of diversion into cost functions. Now, we're going to show that these cost functions belong to certain classes of algorithm speed or just generally resource usage. And proving that these algorithms' cost functions belong to these classes will involve your favorite thing in the world, proofs involving inequalities and quantifiers. So, to motivate this a bit, there's a sort of hierarchy of functions that comes up in computer science and math in general, really. We want to express some sort of notion of functions being greater than or less than each other. We sort of saw a preview of this last class where we subtracted. Is this the one I was thinking of? Oh yeah, it was a whole bunch of slides earlier. I'm not going to look for that. We subtracted a function from another, found that the result is always positive, and thus the function that seems bigger must have a greater value than the other one all the time. That was useful for finding our worst case cost function, but it doesn't really work in general. If we have a couple of functions such that one of them is greater than the other after a certain point, but not always, that idea won't work. But we still want to be able to express the idea that something like n squared is basically always bigger than n. So we're going to make a hierarchy of kind of looks like a tier list too. If we use the less than symbol to informally denote a function being smaller than another, then we know that any constant function, a function that is just one value for all of its inputs, it's going to be strictly smaller than any logarithmic function, because even if this constant function is greater than the logarithm at first, the logarithm will eventually overtake it and stay like that all the time, or forever. Likewise, the same relationship that exists from constants to logarithms exists for logarithms to n raised to any constant power. So this includes square roots and the nth roots and the exponents you're all familiar with. And then going one step higher up the hierarchy, one tier up the tier list, all those functions with a constant exponent are eventually all overtaken by exponential functions, functions where the main expression is still an exponential one, but the base is a constant, and then the exponent is variable. That still is overtaken eventually by the factorial function. So n equals n times n minus 1 times n minus 2 times n minus 3 all the way up to 1, or down to 1. And then even that is smaller than n raised to the power of itself. I'm going to attempt to draw a doodle that will stay on the annotated slides just for reference's sake. So even though the values of them are all sort of clumped together at the start, eventually they form a clear hierarchy of how big their values are after a certain point. Going back to algorithms for a moment, we're going to find that each algorithm's cost function belongs to one of these classes. So if your algorithm has no loops, or at least no loops that depend on its input, takes the same amount of time every time, then we say it takes constant time. It's O of 1, and that's sort of like the best you can do. And then we saw functions already with one loop that goes through the entire input. That would take linear time. And of course, we're going to formalize this, but a good rule of thumb is that if it has 2 nested loops, it's n squared. And we haven't yet seen any code that runs in exponential time, but trust me, it exists. Also, another diversion, this has nothing to do with the class, this won't be on the quiz, but my research, which I think is pretty cool, involves a function called the busy beaver function. And that has the interesting property of it being uncomputable, meaning that there's no algorithm that can ever compute its values for like a given input. And it grows faster than any computable function. So in this hierarchy, you can keep making formulas like, I don't know, n to the n to the n to the n to the n, that grow faster than anything we see here, but you'll never be able to write down a formula that grows faster than the busy beaver function, even though the busy beaver function is still strictly defined for all n. It's pretty neat. Take comp 3030. Now we're going to do a warm-up exercise, and if you've done the readings, you could probably get the right answer. If not, this is going to be pretty much pure guesswork. And that's okay. It's meant to get you sort of thinking about what big O of some function might mean. So I'll just give you 1 minute this time. 1 minute, just think about it and try to guess what the answer is. And if you're looking at the slides, try not to look at the bottom of the slide. I'll start the timer right away. answer is E. So none of these are true. Let's see, algorithm takes exactly n cubed steps. False. The big O notation doesn't mean that, or f of n being in big O of n3, n cubed, doesn't mean f of n is equal to n cubed. It means that it's like sort of in the same growth rate class as n cubed. We'll formalize this, I think, on the very next slide. Likewise for b, big O notation isn't a strict upper bound. We know that f of n has around the same growth or slower than n cubed, but that doesn't mean it can't take any more than n cubed. If f of n were something like n cubed plus 1, that would be fine. C is getting a bit closer to the definition of big O notation, but that word exactly still means that it's, means that that statement isn't true. There is some cutoff and not, so that the algorithm takes around m cubed steps for all n greater than n naught. Again, we'll formalize what I mean by around n cubed steps very soon, but it's not exact. And it's not a strict inequality either. So yeah, it's bounded above by some multiple of n cubed. Let's formalize that. These definitions will be super important. You should probably draw a bunch of red circles and arrows around this slide. I think for Friday's quiz, I won't require you to memorize the definition. But it's quite likely that you'll have to for the exam. If I make a quiz where you have to memorize this definition, I'll tell you ahead of time because I don't want to jump scare you with a surprise memorization question. But even if it's not required, you gotta understand what this definition is talking about. So let's go through it. You have functions f of n and g of n that are defined for all positive integers. This bit, you can probably get away with forgetting. Nah, you should remember. I want to point it out, though, because this is a computer science class. It's not quite all completely abstract math, and this n in the positive integers bit has a very good reason for being there. And that's because n is the size of the input given to our algorithm. You can't have a list of -2 items. That's impossible. You can't have a file that is -20 megabytes, stuff like that. And also, I suppose there may be edge cases where you have input of size 0, such as an empty list. But we find that defining these only on the positive integers can be pretty useful because we're going to do a lot of mathematical expressions and inequality manipulations that only work if n is at least 1. So it's convenient to have n being strictly positive rather than just non-zero. Also, if you're running your algorithm on 0 input, for a size 0 input, it's going to take constant time and not really be worth analyzing further. But whatever. F of n is in big O of g of n. if and only if there exists an m greater than 0 such that there exists an n not greater than 0 such that for all n greater than n naught, f of n is less than or equal to m times g of n. Whew, that's a mouthful, isn't it? These probably seem pretty arbitrary, may or may not be giving you flashbacks to the inequalities we looked at. But all of these quantifiers and like constant multiples and stuff have a good reason to be there. And it's all so we can get a formal mathematical notion of something being less than or equal to something. I'm going to see how simple the first example on the next slide is, and if it's sufficiently complicated, I'm going to try and do a really easy one just for introduction's sake. Oh yeah, this is already getting into tricks. Bleh. We're going to ignore big omega right here for now, but for now know that it's sort of the opposite of big O. It's a formalization of the rough idea of a function being greater than another function. We're going to show first that n is in big O of n squared. So that means, all right, actually before I even get into quantifiers and stuff, I'm just going to draw a picture. So here are coordinates. Here's, I want it to pass the center. Yay. Here's n. And here's n squared. We're probably not going to need to do anything clever with m. You'll see why soon. But what I want to show is that you'd probably want to put n naught around here because for all n greater than n naught, that implies that n squared, n is less than or equal to n squared. So you see, this picture expresses the same thing as the definition is trying to express, which is that even if n is sometimes bigger than n squared at first, after a certain point, n is always below n squared. So anyway, using our definition, also when you're working on questions like these on your own, it really isn't a bad idea to restate the definition of what you're proving for no other reason than because writing something down over and over will help you memorize it. Boom. So this is going to look kind of like other proofs involving inequalities. We're going to start with the inequality that we want to show and sort of reverse engineer it to find a value, find constraints we need for m and n naught. In this case, we're just going to divide both sides by n. Better. I'm going to flip the inequality around so that it's in terms of n. This isn't strictly necessary, but it's much more readable this way. Oh, wait. mn greater than or equal to 1. And then divide both sides by m. With this inequality that we now have a really good idea of what to put for n naught. We'll just say it's 1 over m plus 1. We add 1 just to ensure that n is strictly greater than that rather than greater than or equal to that. And then this example was simple enough that we didn't end up finding any constraints on the value of m. We can throw any value of m in there, and it'll still give us an inequality that gives us a pretty obvious choice for n naught. So I'm just going to choose the simplest positive integer value there is, 1. And that would conclude the rough work that goes into this proof. We have a specific value for m and a specific value for n naught. And then in your formal proof, you would start at n, use the values you found, and show that it's less than or equal to 2n squared. I'll mention again, because it's important, that there is no one right answer for what values to choose here. In particular, n naught probably doesn't have to be 2. I'm pretty sure it can be 1, but 2 is the value that we got from this particular analysis. N being less than n squared if n is greater than 1, and n being less than n squared when n is greater than 2 are both true, so the proof still works in both cases. Likewise, m equals 1 was a total arbitrary guess. I chose it because it would be the easiest to work with. But yeah, we could have multiplied n squared by any integer, any positive number, in fact, I think, and the inequality would still work. It's cool. Now on to a bit more complicated example. We're going to show that n cubed plus n plus 1 is in big O of n to the 4th. I'm going to try and do the rough work just on this slide because adding new pages is such a pain. We rewrite the definition, and then we have an inequality that we want to prove. As usual, we want to start at the inequality that we're given, sort of reverse engineer it to find constraints on n, and then use those constraints we found to prove it formally. You might recognize the rounding up trick from when we were just doing random arbitrary inequalities, and that's a good thing. We were preparing ourselves for big O notation the entire time, it turns out. So recall that the rounding up trick involves taking a complicated side of the inequality and then choosing n large enough that we can sort of just simplify it, find something that exists in between these two sides of the inequality. And in this case, we're going to want to find something larger than n cubed plus n plus 1 that only has one term, so that we can then do some simple division to solve for n with a simplified inequality. Although this inequality isn't looking like it'll work with what I want to do with it. Because what I was thinking at first was that we could just say that n should be greater than 1, as a lucky guess, and then n will be less than n cubed. Oh, it's obvious. Okay. I was scared for a second. I thought I was stuck, but once I started explaining it, I was like, oh yeah, I'm fine, because I am fine. Back on track. Let's guess that n maybe is greater than 1, which would imply that n is less than n cubed, and also that 1 is less than n cubed. And remember, if something is less than another quantity, that implies that it's less than or equal to another quantity. Because with or statements, you only have to satisfy one side of the or for the whole thing to be true. And thus, having just less than means less than or anything else is true, less than or equal. So we turn n into another n cubed, and 1 into another n cubed. I'm just going to see if I could move this over Yeah. I'm doing this so that it doesn't look like we turned mn to the 4 into n cubed plus n cubed plus n cubed, because we didn't. This has nothing to do with this. We got this by simplifying this. Just for the people who are viewing the slides annotated after the fact. Okay, that simplifies n cubed plus n plus 1 into the much easier to work with 3n cubed. So if we could show that 3n cubed is less than or equal to mn4, we'll have basically a much easier time. So for our next step, we could divide both sides by n cubed to get something like 3 is less than m n, and then n is greater than or equal to 3 over m. And then we would be able to choose any m we want, and we would say that n naught is 3 over m plus 1 or something. I don't know, maybe. But this example does a somewhat sneakier trick that results in a bit more, somewhat more elegant solution. Because it's kind of gross how we have this fraction here. Everyone hates fractions. The trick in question is that it sort of does a rounding trick a second time. N is greater than 1, which implies that n is less than n cubed, and that 1 is less than n cubed. It also implies that n cubed is less than n to the power of 4. This is a perfectly fine thing to do. Remember that our goal with the simplification thing is to find an expression that is between these two in terms of being like greater than or less than parts of the inequality, in between the two, and easy to compare with the simpler side. So now we have the simplest thing of all, because we can completely eliminate n to the 4 from this inequality, and that'll let us solve for m. And I think this is a better technique to do in general, just to find a specific value for m for proofs like these, because I kind of got lucky this time and earlier in this example when I was able to find something that would work for all m. In most cases, we're going to have to find specific m. Anyway, let's divide both sides by n to the 4. And now we have m is greater than or equal to 3. Now we have a constraint on m, and as we saw earlier, a constraint on n. Excuse me. And that actually makes us ready to do the formal proof. Because from these constraints, it's really not that big of a jump to find a specific value for m and a specific value for n naught that gives it the desired inequality. I'm just going to rewrite this sign to be a bit clearer. Yeah. Kind of looked like an equal sign back there. I'm going to go over the formal proof this time because I've been sort of glossing over those in previous examples, and those are the parts that actually get you marks. You could be the best in the world at doing this rough work, but it wouldn't get you anywhere on assignments because it's all meant to be foundational for the formal proof. So let's look closer at the formal proof this time. We start by defining specific values for the existentially quantified variables. So there exists an m and there exists an n naught. And we just take these directly from the constraints we just found. M has to be greater than or equal to 3. What's the simplest value that satisfies this constraint as well as the definition m is greater than 0? Well, it's 3. Oh, easy. N naught has to be greater than 0. N has to be greater than n naught. And n has to be greater than 1. And we can satisfy all of those constraints by just setting n naught to 1. And then, this is just good for style points, restate what you're going to show. We're going to show that for all n greater than 1, that comes from for all n greater than n naught, the given inequality is true. We let n greater than 1 be arbitrary. Again, this comes from the universal quantifier. And then we start with one side of the inequality that we were going to show, and show that using one side of the inequality and the specific values of m and n naught that we found, then the other side must be true. In this case, n cubed is less than n to the 4, n is less than n to the 4, and 1 is less than n to the 4, which we mentioned here. We can easily turn one side into the other. So yeah, the rough work and all the tricks that go into it can be really weird. Might mention this a couple of times, but pretty much all the math, all the algebra you've done, I'll get to this in a moment. Everything you've done up to now has been about equalities, equal signs, and inequalities follow different rules, and they're another thing you'll have to get used to. Did you have a question? Ooh, probably made a mistake here. So you're wondering how this is reconciled with this? Mm-hmm. Okay, yeah. Thankfully, that's not a mistake, but it is a lack of detail on my part. I found the constraint that n has to be greater than or equal to 1 over m, and then used that to define a specific value for n naught, which was 2. And then my next step that I would do in my formal proof would be to say let n naught equal 2, and then let n greater than 2 be arbitrary, similar to what we did here. And I would also set a specific value for m, m equals 1, as shown here. You're right that this constraint wouldn't work with this value of n naught for all m, but luckily m is existentially quantified, so we just choose m equals 1. Does that make sense? Even if it doesn't, it probably will later. This stuff needs time to sink in. So yeah, I think we're done with this one. Now we'll show that n squared plus n is in big O of n squared. So how are we going to do this? Probably another instance of the rounding up trick. Let's try it. I want to find something that is greater than 3n squared plus n that is more easy to compare to mn squared. And then I want to find that simplified expression and show that it's less than mn squared, because showing that inequality will imply the original inequality. This is thankfully another easy example. As long as n is at least 1, or no, greater than 1, then we'll be able to turn n into n squared in our simplified expression. Now we have 3n plus n is less than 4n, or 3n squared plus n is less than 4n plus squared, 4n squared. If we can show that 4n squared is less than mn squared, then we'll be able to find values of n naught and m that work for the original inequality. So let's do the same thing we did before, sort of assume the inequality that we want to prove, and then reverse engineer it to find values that work. And you can probably guess what's going to happen next. It's another nice and simple as you can get with these kinds of questions. Sort of inequality. We're just going to divide both sides by n squared and get that. In more complicated proofs, you'll likely find some sort of constraint, some other constraints on n, but thankfully this time we just have m is greater than or equal to 4 and n is greater than or equal to 1. And with those in mind, we can choose specific values. M is equal to 4, and n naught is greater than 1, because n has to be greater than n naught, and we already saw that n is greater than 1. And that makes the rest of the formal proof pretty elegant. Restate what you were going to say, and then now that you've reverse engineered the inequality by assuming it and finding values for n and m that work, then do it the right way and start with one side of the inequality and use those values to show that in this case it's less than the other side of the inequality. That's just an application of the rounding trick. I'm not going to do any further examples in this class. I'm just going to briefly talk about the quiz and then let y'all go. I haven't made it yet, but I'm planning to have it include one question about cost functions and counting steps, similar to the one on last week's quiz, except this is going to include at least one if statement. It's crazy. And then the other question, I'm planning to have something relatively simple on big O notation. We won't have anything about big omega or any of the other asymptotic notations. It'll be something as complicated or less as the things we did today. Good luck studying, and I'll see you all on Friday.